This was the 4-bit register that we
जी
studied. Then this serial transfer from register A to B, this occurred with the help of those 4-bit registers, 4-bit shift registers that is visible in front of you right now.
तो सर ये वाली स्लाइड होगी थी।
जी जैन क्या कह रहे हैं?
सर ये वाला आपने करा दी थी, ये वाली स्लाइड।
ये वाली हो गई थी और सीरियल ट्रांसफर ये भी हो गया था.
यस सर, ये दोनों हो गई थी।
ओके ओके. So, just for an overview of what we did in the last lecture, for the people who were missing, we studied about registers after this 4-bit register that has parallel load, and what is the difference between a register with a parallel load and a serial transfer load. This is that in a single positive edge of the clock, a single positive edge of the clock transfers all of the input bits to the output. So this is the clock which is connected to all the D flip-flops, positive edge trigger D flip-flops over here. So these clocks at once, when they get the single positive edge over here, over here, over here, and over here, the single positive edge transfers A0, A1, A2, A3 and new to the new output levels in just a single positive edge. This is the parallel loading. This is the parallel transfer. In the same circuit, we added a load circuit. And why this was added? This was added so that we can have, if we turn the load equal to 0, we can have A0, A1, A2, and A3 retained to the original states so that the circuit retains memory. Then we discussed that we do not play with the clock. We do not add gates to the clock because this adds delay to the circuit. And since we'll have millions of gates, millions of D flip-flops attached to a single silicon chip that we call ROM, that we call PCB, that we call motherboard, and in those millions of circuits, if we add a little delay in the clock circles, in the clock cycles, then this little delay, even if it's in femtoseconds, microseconds, or picoseconds, this little delay can cause in loss of synchronization, and this loss of synchronization can result in loss of data. And this loss of data will ultimately lead to corruption in system, which is basically not tolerated at any level. So we want the clock level to be synchronized, and we want the clock to be untouched till it reaches the D flip-flops. That's why we just add circuitries to the D inputs of our D flip-flops so that we can hold the outputs over here through the input D, and we do not change the clock C. Then we moved on to 4-bit shift register, and in this 4-bit shift register, the difference between the parallel transfer and the serial transfer was that in a single bit of in the single positive edge of the clock, only one bit is transferred. If we have 4 bits, then we will have to wait for 4 positive edges of the clock, and in each positive edge, 1 bit would be transferred. So 1, 1, 1, and a total of 4 bits would be transferred after 4 positive cycles, because at this output, the serial output, after each positive edge, we have a single bit coming out, either it's 1 or it's 0. So at 4 positive edges, after 4 positive edges, we'll have 4 bits at the output. So in parallel loading, we had 4 bits that were being transferred at once. And in serial bit transfer, we have this circuitry where we transfer bit by bit the input to the output. The thing that needs to be remembered over here is that this system is slow. This will take 4 clock cycles to make the 4 bits reach the output, whereas this system is quite fast. This would make only one positive edge lead to the input transfer to the output. So there can be 100 bits, 1000 bits, but the only positive edge cycle would be that is needed would be 1. Whereas in this case, if we have 100 bits, if we have 1000 bits, we would be needing 1000 clock edges or 100 clock edges as per the case. Whereas the positive thing, the profit that we have while implementing these circuits is that the circuitry needed for these circuits is inexpensive. It's quite a lot cheaper because we would be needing 1,000 D flip-flops for 1,000-bit data to be transferred to the output over here. Whereas in this case, we do not need 1,000 D flip-flops to reach to the output. You can have even a single D flip-flop or two D flip-flops, and you just need to transfer the input to the output turn by turn. The only thing that's needed more over here is the number of positive edges of the clock. This was an example that we studied for serial transfer from shift register A to the shift register B. So this serial transfer occurred in this way that's in front of you in this diagram. Now we are going to discuss the serial adder. We have a shift register A and a shift register B in front of you. The contents of A, we are going to add the contents of register B to the contents of A, so that the sum at the end is going to be present in the shift register A. I want all of you to look at this first closely, and then I would want that somebody explains me that how is this transfer, how is this addition going to be placed over here, take place over here. This is shift register A, this is shift register B. At each clock edge, one clock edge, if we had 1, 0, 0, 0, and we had 0, 0, 0, 1. So at each positive edge of the cycle, the least significant, that is this 0 and this 1, they would move to the cleared full adder. The cleared full adder means at the start, the full adder would have been resetted. So a 0 would reach at the X, a 1 would reach at the Y, and since if there was no carry from behind the circuit, then we'll have no carry at the output at the start, so we'll have 0. Now I want any one of you to explain what's going to happen next. Yes?
सर थोड़ा रिवाइज कर दें पीछे.
What should I revise?
सर ये आपने जो 100 या 0001 वगैरह लिखा हुआ है, इसका क्या मतलब है, क्या चीज है?
We have this 4-bit register. Okay, 4-bit shift register, exactly this one. This 4-bit register is present over here and is present over here as well. So this 4-bit register that is in front of you over here, the serial input, serial output, that's the same, the serial input, the serial output. At each positive edge of the clock, 0 is going to be, for the first positive edge, this 0, for the second positive edge, this 0, for the third positive edge, this 0, for the fourth positive edge, this 1 would be going at the output. Similarly, for the first positive edge, this 1, then for the second positive edge, this 0, then the third, this 0, then the fourth, this 0 is going to be at the output D of the circuit, turn by turn. So for the first positive edge, X is going to be 0, Y is going to be 1. For the second positive edge, X is going to be 0, Y is going to be 0. For the third one, 0, and again 0. And for the fourth one, we'll have a 1 over here and a 0 over here. So turn by turn, at each positive edge of the clock, X and Y are going to be updated according to the register, shift register A and B contents. Is this clear? Okay, let's have a look at this example. For the first positive edge, if we have 1, 0, 0, 1. Okay. So the first thing, at the first positive edge, X is going to be 1, Y is going to be 1, Z is going to be 0, assuming that there was no carry coming from the previous circuit. Okay. Now tell me that what is going to be the value of sum S at the first positive edge?
0.
Very good. What is going to be the carry?
1.
Very good. So 0 is going to appear over here. And this one is going to be removed since this one has moved to this position. And this one is removed as well. Now we are at the second positive edge. Now at the second positive edge, a 0 comes over here and a 0 comes over here as well. Now, please tell me, at the second positive edge, what is going to happen? Since we'll have a 0 at x, a 0 at y, and what would be present at z at the second positive edge?
1.
Very good. So what's going to be present at sum now?
1.
1.
1 0 again.
0.
So we'll have a 1 over here. Since it's going to be traveling back, this 0 is removed. Similarly, this 0 is removed as well. And we have the carry 0 now. Now, at the third positive edge, we are going to have a 0 over here, a 0 over here. So what's going to be the carry now?
0.
0.
So this 0 is going to be present at z now. What's going to be the sum now?
0.
What's going to be the carry?
0.
So this 0 reaches here. And we have this third bit removed as well. Now, the fourth positive edge, the last positive edge. What's going to be present at x? 1. At y?
0.
At z?
0.
So a 1 would come at the sum and a 0 would come at the carry, right?
Yes.
So we have 1, 0, 1, 0 at this place now in the shift register A, which has the updated contents. Where did we start? We started at 1001 in A, and we had to add the contents of B, which was 0, 0, 0, and 1. So what's going to be the sum anyways? It's going to be 0, 1, 0, 1. And that's the same content that is available to us in this shift register A. Is that right?
Yes, sir.
Okay. So one thing that you should remember, we have performed 4-bit addition prior to this as well. If you remember, in chapter number 4, we had added 4-bit numbers through adders, which was a part of your mids exam as well. You remember?
Yes, sir. Yes, sir.
What was the difference over there and over here?
सर वो 1 by 1 ऐड हो रहा था यहाँ पर.
Yes, that one was being added in parallel in just a single hit of the clock. There was no clock needed. That was being added in parallel. You add the number in both the registers and you get the output. But over here you have a difference. What difference do you have over here? Difference is for adding 4-bit numbers, we had to toggle the clock 4 times. We had to have 4 positive edges of the clock. Am I right?
Yes, sir.
So we needed 4 positive edges of the clock in order to maintain the sum in the serial register A. Yes, Zainab, we are adding in sequence over here right now. Whereas in that circuit, if I can open that for you, just a second.
एक मुझे छोटी सी बता दे पिछली स्लाइड में जो 7th स्लाइड है
This one?
जो सर अभी हम कर रहे थे। यस सर, जो अभी कर रहे थे हम। सर इसमें सर इस सम कैरी की समझ आ गई। जो हमारे पास ये नीचे किस तरह हमारे पास की वैल्यू आती है z की वैल्यू सर।
Z is the carry that is basically transferred from the previous output through D flip-flop to the next input. We want the previous carry to be added in the next sum. So for that thing, we latch this carry in this D flip-flop, and in the coming positive edge of the clock, this carry, if for example, in the previous sum, the carry was 1, then we need to transfer this carry to the next input. And how do we do that? We do that with the help of the second positive edge of the clock. When the next positive edge of the clock will come, this 1 from the D would come to the Q and to the Z. So this one would appear over here in the next sum, which is exactly the thing that we did in 1 0 0 1 0 0 0 1. Now see, if we have this 1 1 sum equal to 0, the carry needed to be added to the second sum, which is over here.
Yes, sir.
That's why we have this D flip-flop over here. Okay,
Okay. Thank you.
is this clear now?
Yes, sir.
So what did we have over here? 4-bit binary adders. So in the 4-bit binary adders, we did what? We added the two 4-bit numbers at once. So we did not need 4 positive edges of the cycle, of the clock cycle, and we did not add them turn by turn. All of them were being added at once over here in this circuit. Whereas if you can have a look at this circuit, which we are studying right now, which is through the addition through the full adder, the serial shift register A and shift register B. In this circuit, what do we have is that we are adding the numbers present in shift register A and B in a sequence, turn by turn through the 4 positive edges of the clock. Is this clear?
Yes, sir.
Yes, sir.
Okay. Anything that that needs further clarity over here? Any question?
सर जो क्लॉक पे जा रहा है डी फ्लिप फ्लॉप की
Yes.
वो जो एंड लगा हुआ नीचे सर इसकी समझ नहीं आ रही।
Okay. The first thing is that we need the clock, the same clock for each of the circuits, right? यहाँ तक ये बात clear है?
यस सर।
Okay. So from this circuit, we came to know that we only need to shift register A to B when we have this clock and shift control both active. Only then the shift register A content should be transferred to the shift register B. Now, if you have a look at this circuit over here, this means that shift register A and shift register B contents, they need to be transferred along with the clock, and one thing that needs to be added in the full adder along with these two contents is the carry, and this carry needs to be added the same time when we had the previous outputs coming into this full adder. So we have to make this D flip-flop clock in coherence with the next inputs of shift register A and B. If clock and shift control, both of them are not active, then this D flip-flop should not transfer this one over here, if it is a one over here, to the one here. If clock is not active and shift control is not active, then this one should not be transferred to this Z. This should only be transferred to Z only and only when both the shift control and the clock are active. This would mean that we are transferring the next bit to X and Y. And at that time, when we are adding X and Y over here, only at that time, we need to transfer this D to Q. So that's why we have implemented a gate over here for this D flip-flop, which tells us that yes, shift control is active as well as clock is active. So if you had a carry from the previous calculation, you need to move it to the Z value. Is this okay now?
सर मतलब शिफ्ट और क्लॉक जब
Yes,
हमारे
sir.
पास ऑन होगा तब हमारे पास Z के पास वैल्यू जाएगी.
Yes, जिस वक्त शिफ्ट और क्लॉक बोथ एक्टिव होंगे, सिर्फ उसी वक्त यहाँ पर शिफ्ट होगा. ये बात हम यहाँ से भी क्लियर कर चुके हैं. जब हम शिफ्ट को भी एक्टिव करते हैं और क्लॉक को भी
Yes, sir.
एक्टिव करते हैं, तब वैल्यू यहाँ से यहाँ जंप करती है, यहाँ वाली यहाँ से यहाँ जंप करती है और यहाँ वाली यहाँ से यहाँ जंप करती है. सिमिलरली
Yes,
यहाँ
sir.
पर हमने इसी बात को यहाँ देखा था कि शिफ्ट IA सिर्फ उसी केस में यहाँ से यहाँ शिफ्ट करती है वैल्यू को, जब आपके पास यहाँ पर 1 0 व्हाटएवर यहाँ पर आया होता है और ये वाला क्लॉक भी आपको पॉजिटिव एज प्रोवाइड कर चुका होता है. सो इफ क्लॉक इज एक्टिव, ओनली इन दैट केस वैल्यू यहाँ से यहाँ शिफ्ट होती है. इज दिस ओके?
Okay, sir.
कोई कंफ्यूजन यहाँ पर?
No, sir.
मतलब सर मतलब पूरी कैलकुलेशन हमारी होगी तब जब शिफ्ट और क्लॉक ऑन होगा.
यस 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 यस
वरना वैसे तो कैरी अगर नहीं जाएगा फिर हमारा आंसर गलत आएगा.
यस 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 यस.
Okay.
इज दिस ओके?